Okay, so this is exam 3. I'm going to go through here and just take this and try and explain a little bit as I'm going through. If you haven't done so already, you should either have your exam back or obtain a copy from the stats portal. So anyway, the first one says the value of t star, the confidence coefficient. That means it's coming from the table. Remember, when we do a confidence interval for the t, it's going to be the statistic x bar plus or minus t from the table times the standard error, which is going to be s divided by the square root of n. But they're just asking you for this value of t right here for a 95% confidence coefficient and 10 pieces of data, or n is equal to 10. So remember, the degrees of freedom is n minus 1, and which is 10 minus 1 is equal to 9. So now all I have to do is pull out your t-table, and you get to the t-table, go to 95% confidence interval at the top, and then go down to 9 degrees of freedom, and the confidence coefficient is 2.262. Number 2, for small samples, t intervals are wider than z intervals based on the same data set. Now, there's a couple of ways you can either know or figure that out. One way to just figure it out is if you go in any one of the columns on the t table. If you go to the bottom row, it's and just look at the confidence level for, you can do it for any one. Let's look at 95% since we just did a problem with that. For the z value, you're going to have x bar plus or minus 1.96 times the standard error. And for the t, you're going to have x bar plus or minus some t value for a small sample times s divided by the square root of n. So that's 1.96. If you go to 95% and go to small sample sizes, you're always going to get a t value that's larger than 1.96. Therefore, the interval is going to be wider. So that's one way to figure that out. Another way, and this is more just a reasoning kind of way, when you do a z value, you know the standard deviation. So you have a population standard deviation. You have some information. Well, when you take the sample standard deviation, in fact, the smaller your sample is, the less information you have. And so when you have less information and you're making a confidence interval, with less information, you're always going to have a wider interval. You have less certainty, and so the interval is going to be wider there. So in number 3, I'll tell you, I kind of made a mistake on this one. It's everything is the way it's written here is exactly like it was written in the. In fact, the first 5 questions on this test all came from the quiz banks on the stats portal for the 4 chapters of this test. Well, anyway, this is exactly the problem, and it said use the conservative value. That's in your textbook, and it's not the value I'm going to use. In fact, no one uses that anymore in a real statistical test. So that's why we went to the calculator and said no to the pooling. By the way, if you looked at my last video, and I'll write about this, I typed it wrong on the table. The non-pooled test, you answer no on your calculator. In fact, we'll only answer no on the calculator for our test. So anyway, I meant to just X that out and use the calculator to get this. And if you did that, you would go to stat, t-test, and put your numbers in. You should get a p-value of 0.04869. Anyway, that is between 0.05 and 0.01. And I didn't want to penalize anybody who did read the book. If you'd used the conservative value, I'm pretty sure you would have gotten A. So I threw that one out on the test. But there's how to do it if it comes up in a problem next time. And I'll try and pay more attention and X out that part about the conservative value stuff. Okay, so on number 4, so you read this article and it tells you the p-value is 0.05. So that means you have a non-significant result, sometimes abbreviated NS, non-significant. And I want to know if they're significant at the 10% level or 0.1 level. Well, all I know is that the p-value is greater than 0.05. I don't know if it's 0.07 or 0.34. So it might or might not be significant if not significant if I know it at the 0.05. So there's not enough information to answer that. On number 5, we have a poll that says 54% of 600 people favor incumbent. Shortly after that, it's disclosed that he had an extramarital affair. This was in the test bank, and I'm not sure when it was written, but that seems to be happening. Well, anyway, a new poll finds that 50% of 1030 now favor the incumbent. We want to know if his support has decreased. So, yeah, we're going to have to do a little bit of math on this one. But you can always do it by hand and not do as much. But 0.54 times 600 means that was 324 out of 600, and that's where they got the 0.54. And now that's really not what we're looking at. We're only looking at in this one sample that we have now, but that's where they got that from. In this one, we had actually, I could see this being worked 2 ways. Let's do this as a two-sample test, and we'll see how that works out for us. Anyway, we had 50% of the 1030. That would be 515 out of 1030. And that's the 50%. So using the two-sample proportion, two-proportion z-test, go to stat test, two-proportion z-test, and put 324 out of 600, 515 out of 1030, and then put has it decreased, so less so the first one greater than. If I had done this less than, so we want to know if this is the smaller, so put in greater than and calculate, and they get a z-value of 1.5. Yeah. It seems why some people might have missed this. The research hypothesis, if we're looking at the second one, would be P2 less than P1. And if you did that, you get minus 1.55. But if you set it up as the first one greater than the second one, you could have said that was P1 greater than P2, and you would have gotten positive 1.56. Yeah, if that happened to you on this test and you're not going to retake the test and score higher, come by and see me, because that could be, depending on how you set the hypothesis, it really does imply the less than, but you could set it up the other way too, and it doesn't really tell you there. That's one advantage of having me take the test. I might find another way to do things here. In fact, I can think of another way to construe this problem. that one comes out to be minus 2.57. Well, that's interesting. See, you could have taken this, and I'm going to go ahead and put it on here. Looks like they gave you three answers that I guess could all have been correct depending on how you construe the problem. If you just look at this as only one sample right here, you could, it's reasonable, I think, to say that the research hypothesis is that P is less than the 0.54. This is really a separate sample at another time. And so if you did that, then you would do a one sample z-test, and in your calculator you would put just this would be your only sample, 515 out of 1030, and your HO would be 0.5. And if you do that, you're going to come out with minus 2.57. Fantastic. That one was in the quiz bank, and again, I just think that can be construed three ways. So anyway, if you had one of the answers that got wrong on that, let me know and I'll give you a credit. Okay, so number 6. Hopefully we won't have a lot of other problems that have more than one way to interpret the problem. Well, anyway, number 6, we're going to estimate the population mean. We have a random sample of 400. The sample mean is 73 to 20, and the sample standard deviation is 4,400, and we want 99% confidence. Since we have S, this is T. There's just one sample here. You could work this out this way. You could do X bar plus or minus T times SX bar, and you would have then 73 to 20 plus or minus, I'll look up the T in a minute here. Well, actually, with N of equal to 400, you're going to have to go down to the bottom of the table and use the 2.576 as, because our degrees of freedom don't go further than that. So when we get beyond 100 degrees of freedom, we'll just use the value at the bottom, the same as the Z, times 4,400 divided by the square root of 400. And using this, that's 566.72, which is pretty 566.72, which is pretty close to this one. Now, there's going to be a little bit of a rounding because even at 400 degrees of freedom, that's not going to exactly equal that. Well, not only that, I wrote down 70. Well, that's not going to make any, but that would be 220 there. So the other way to work this one out is just to use your calculator. In fact, that's the way I did it. Stat, tests, t-test, and stat, test, t-interval. And then the x-bar is 73 to 20. The sample standard deviation was 4,400. Sample size 400. And we're doing a 99% confidence interval and calculate. And when you do that, you get 70 to 651, 70, 737.89. And if you just subtract, since that's the lower and upper limits, if you just get the difference between either one of those and 73 to 20, you will get 569. number 7, you see you got a first and a second score there. That's like before and after. Okay. That's not what I wanted to have happen. Okay. B, the matched pairs t-test. And then in 8, so we want to know if, well, actually this is going to be more appropriate in the second part for number 9. We want to know if the proportion is lower than the national average. So HR is going to be P less than that national average of 0.41. And let's see, we have 348, 132 out of 348. And this is one proportion, so easiest thing, use your calculator, stat, test, one proportion Z interval. And then we've got 132 out of 348. 95, calculate, and that's 328 to 430. That's A. Now I'm going to go ahead down and do the next part here. Now we're testing the hypothesis, and we want to get the p-value. So just go stat, test, one proportion Z test, and make sure you've selected, you've got P 0.41 in the PO, 132 out of 348. You've selected less than. Calculate. The p-value is 0.122. And that's going to be answer B. I'm going to go ahead and just write that. I've got it on my table here. Because that's between 0.1 and 0.15. Let me, before I move on to the next part, say that you could have done this in a little bit longer way here. 132, I'm going to go ahead and just put it down here. 132 divided by 348 is 0.379. So we could have gotten this as p hat plus or minus z times the standard error p hat q hat over n. So we would have 0.379 plus or minus, for 95% that's 1.96, the square root of 0.379 and 1 minus that, which is 0.621, divided by the sample size of 348. And so I'm just going to put that in my calculator. Of course, you can do it with your, just with the testing step and test procedure on your calculator, but if you'd prefer to work them out, that's certainly okay as well. And working that all out, I do get 0.328 to 0.4299, or about 430, so we got that right. And yeah, we could actually do the p-value by hand too. I'm going to show you how to get that started and then let you finish it if you'd like. So remember, your test is then equal to statistic minus the hypothesized parameter over the standard error, pH, QH over N. So that's the 0.379 minus 0.41 divided by the square root of, remember when you do the test statistic for proportions, you use the hypothesized proportion here, not the sample proportion, and that was 0.41, 0.59 over the sample size of 348. Get that to be about minus 1.18. When I did on the calculator, I got minus 1.16. That's probably just rounding error. Yeah, the rounding error would be over here because that 379, and your calculator's not going to make any of this rounding. It's going to have some more numbers on it. Well, anyway, if you did this, you could then take this z value. I don't expect anybody to do this, but you could, and go to your z table at minus 1.18, and then just look this value up in the table. And again, you're just going to get an estimate of what you would on the calculator, but it ought to be between 0.10 and 0.15, that's for sure. And you could have either used that or this, but if you did it completely by hand, that's what you would do if you did the rounding that I did. Okay, so on number 10, we've got a confidence interval here for the difference between two proportions. Well, first of all, I'm going to go ahead and, yeah, that's back now. First of all, I'm going to try and clear all that out. Getting a pattern on this. Okay, so anyway, in our first sample we had 64 out of 100. That's just X and N and group 1, I'll call it, since that's what it's here. So in group 1 we had a p-hat of 0.64. And for group 2 we had 80 out of 100. That's 0.8. So remember, our statistic is going to be p-hat A minus p-hat B. That's going to be 0.64 minus 0.8. That's minus 0.16. So plus or minus. That's a plus or minus. Z times the standard error. I'm not getting this to right where I want it to. That should be p-hat 1, q-hat 1, and I'm not being able to get that to work out very well for me right here on the screen. p-hat 2, q-hat 2 over n2. So that's for 95%, you're going to have 1.96. That's going to be the square root of 0.64, 0.36 over 100 plus 0.8, 0.2 over 100. And that comes out to be 0.122. Okay, the other way you could have gotten that is to do stat, tests, and this is, well, I guess either one would be fine, 2 proportion z interval, and just put the 64, 100, 80, 100, 95 in and calculate, and you get minus, okay, that's not what I wanted, minus 0.2825 and minus 0.0375, and remember over here we got the minus 0.16, so we're going to take that top thing and subtract a minus 0.16, and if you do that, 0.0375 minus a minus 0.16, of course you could have just said plus 0.6, I'm sorry, I put in a number wrong here. And I get 0.1225, so there we go. Okay, so on 11, we want to know if we have enough difference to see if there's a difference, and that's a two-tailed test, and of course gives you that right there. So stat, test, 2 proportion, z-test, and make sure you have selected not equal to. Sorry about the extra sound effects there. I don't know if you guys are getting those or not. But anyway, the p-value is 0.0117 on my calculator, and that is between here and here. I got 0.01174, You could work this one by hand too, getting the working out the z-test and all of that, and then using the z-table to get your p-value, but that seems like a little bit much even for me. But you could do it. Number 12, anyway, we have a sample of 1,000. You can see I'm not going to do it. And so anyway, we want to get now we want to do a 90% confidence interval, but we just want to get the standard error. Remember, if we're doing a confidence interval for one proportion, that's the qualitative variable. They're either in favor or they're not. So it's going to be p hat plus or minus z times p hat q hat over n. And so it's just asking for this part, the standard error. And p hat is going to equal, what did I put here? This should have been 800 out of 1,000. So p hat was 0.8. That's just 800 divided by 1,000. And so I need the square root of 0.8 times 1 minus that. The q is just 1 minus whatever the p is, divided by 1,000. And I get 0.0126. I'm going to round that up to 0.013. Okay, so clearly we have two samples here, and we're talking about means. After all, it says means. But anyway, first question is the sample size large enough? The smallest sample size here is 12, so that is going to depend on whether or not we have skew. What's the parameter? Remember the parameter, we're talking about means, so it has to be means. The parameter is mu, and we've got a difference between two of them. That's mu A minus mu B. The upper and lower confidence limits are 0.611 and 2789. Are you confident that females are charged more? Yes, because the entire interval is greater than 0. So they're charged somewhere. This is a little bit incorrect to say it this way, but you can think of it as between $6 and almost $28 more. Remember, the real thing about confidence intervals is not about one specific interval, but about the collection or the procedure through which you collect, which you could, if you cared to construct many confidence intervals. But it's really a statement about the procedure or about the many confidence intervals. So anyway, the number 16, we're going to get the p-value. And let's remember that this is a one-tailed test because we want to know if P1, or P for females, is greater than the proportion for males. So stat test, two-sample t-test. Put the numbers in, make sure you select greater than, leave it as not pooled, calculate, and I got a p-value of 0.002. So we're down to A or B. Now if you'd put not equal to in there, you're going to get 0.004. So that was the distractor there. P-value is small, that's less than alpha, less than any alpha we've used. And so we can be confident. This is a really low chance that we would get this result, this big of a difference, simply by chance. So we can be confident that females are charged more than males. Okay, so we've got a before and after thing there. It's matched pairs. The parameter is It's good to see the marker come up. Mu. This is just one sample. So if we were, depending on which way we want to subtract, I would go after minus before, 3, 2, and so on. But the key is that there's just one sample. Okay, a 95% confidence interval goes from -1.5 to -0.096. Which of the following is the most accurate interpretation of the interval? Remember, this is not about one interval, so it's not A. Both B and C say the process, so it is that. Remember, repeat over and over again. 95% of the intervals, that's okay, would include the real population parameter. Remember, it would be 5% that don't. Okay, now so we've got a random sample of 150 DVDs. The sample mean price is 15. The sample standard deviation. Can we conclude that the population mean is less than 16? And we've got mu is equal to 16 for HO. So your HR is over here, always about the parameter. All your hypotheses are about parameters. But what you want to include in the research hypothesis, we want to know if the population mean is less than 16. Okay, we have means and standard deviations here, 150 DVDs. It's large enough. Remember, even once you get above 100, it doesn't even make any difference if there are. I don't know why I'm having to close this twice every time, but the answer anyway is yes. So we have the 100 DVDs now. The sample mean is 15, and we want to know if we can conclude that the population mean is less than 16. That number 16 is the hypothesized parameter. We don't hypothesize statistics ever, and we're not going to compute parameters. So you either compute the statistic, that would be the 15, or your parameter is the 16. So on number 22, we have a sample size of 50. That's an asterisk, which is an extreme value. So it's not large enough because we need at least 100. And I know some different programs do different things here. The program I'm using, and which we'll use here, started a little bit in the day class already. We'll go into this in the night class or the MT1 class. But remember, if we go more than, let's see, I should have gotten 1.5 of those. Well, I'm not doing a very good job at drawing here. That's supposed to be about 1.5. It must be pretty close, actually. But it's an asterisk, and I've been telling you that. Asterisk is extreme value. And you need at least 100. So we've got a random sample of 100 from plan A. 8 are defective. This is a qualitative variable, so we're talking about proportions. In the second group, a random sample, 4 are defective. That means we only have 4 yeses. That's not enough. Doesn't have anything to do with skew, outliers, or extreme values. The yeses and nos have to both be greater than 5. They're not. Okay, this is just testing the idea of confidence intervals again. It's about the process. If we keep drawing samples over and over again, 95% of the confidence intervals would include the true population parameter. It's not a statement about one interval. Okay, I really don't even have to read the problem on this one. We're talking about p-values. It's always if the population whatever is something, then there's a p-value chance of obtaining a sample statistic this extreme or further extreme. That's got to be D. Yeah. That's awesome. I'm going to clear this off again. Well, actually, I'm not. The answer was D. In 26, random sample of 100 civics. Actually, remember I changed that to both of those to 2011s. But anyway, there's the sample mean and sample standard deviation. We want to know if they if the average price is less than 20,000. We have sample standard deviation, one sample. That's just a t-test. The second one, which selection is, we want to know how much more does one group spend than the other group? How much more? So that's a quantitative variable. We're talking about means. There's two samples. That's a two-sample t-test. Scoot this up a little bit for the next one. Which of those intervals would lead to us to reject in favor of the 5%? Well, you reject when the interval doesn't include 0. There's a difference. If it includes 0, I'm sorry, if it includes the parameter. I was thinking about one of the other problems. Anyway, this is p equal or not equal to 30. If it includes 30, you would fail to reject. But we're looking for a reject. Option B does not include 30. That's it. Okay, number 29, we're going to estimate the population proportion, and we want to know what size sample we need with, if we want a margin of error of 0.3. So remember, when we get around to doing a confidence interval, it's going to be p hat plus or minus z times the standard error. And this right-hand side is the margin of error. So we can set the margin of error, the 0.03 is equal to this right-hand side. Z is going to be 1.96. That's for a 95% confidence interval. We're looking for n, and it says we have no idea the value of p. If we had a pilot study, we could put that value of p in here. We don't. If you don't, the largest product of two numbers that sum to 1 is going to be 0.5 times 0.5 or 0.25. So now I'm just going to solve this equation. N is equal to 1.96 divided by 0.03 squared times 0.25. And I get 1066.1, round up to the next number, that's 1068. If we yeah, well, how about that? If you have a pilot study, it's this. Unless it just happens to be 0.55, this number is going to be smaller. So like if you had, in here 0.6, 0.4, that's going to be 0.24. So any other combination is going to be smaller, and so that is also going to be smaller. And I believe that was marked wrong on the key. Null hypotheses are statements about population parameters, always. which of the following would produce the largest value for an independent measure's t-test? So you want a large difference between means. The largest is going to be 10 minus 20 divided by the smallest standard error. Remember, that's the square root of s squared 1 over n1 plus s squared 2 over n2. And so the smaller those are, the bigger the number is going to be. And so the smaller variances are here with the larger differences. That's C. This is interesting. Okay, I'm not sure why it finally came. Yeah. Okay, I think we've got it now. Okay, so we have a random sample of 250 high-level female employees. 62 stated they'd been sexually harassed on the job. That's qualitative. Either they have or they have not been sexually harassed on the job. And we want to know if we can conclude that less than 30% of that population has been sexually harassed on the job. That's a qualitative variable. It's binomial. And we want to know if we can conclude that the population proportion is less than 30. There's never any equal sign in a hypothesis, just less than 30, and of course it has to be about a parameter, that's p, not p hat. A result is called statistically significant whenever the p-value is less than or equal to the significance level. You might want to say of the B, that's sort of the only other response in there that might be worth considering. When the research or alternative hypothesis is true, well, even if you reject HO, even though you're confident that it's true, that doesn't mean that it is true. There's always a chance of error when you do a hypothesis test. So on 36, remember this, I think is about the third time on this test. Maybe I overdid the confidence interval interpretation. But anyway, I eliminated B because we haven't talked about type 1 errors yet. Not sure we'll get to that this semester or not. Really, the type 1 error is just whatever your level of significance is. It's the chance of making an error before you ever do the test. You're willing to accept that level of error. But anyway, it's not C because that's just about one thing. So remember, it's always about the procedure, the process of collecting many intervals if you were going to do that. And you know, it can't be A. Confidence intervals are always going to cover the sample mean because the sample mean is the center of the interval. We want to know the probability that the procedure provides an interval that covers the population mean. Okay, so this is a matched pairs problem. You can see the before and the after, and we've got a quantitative variable there. Sample size large enough. There's really only one sample, and it's a size 7. So it might be large enough, but only if no skew, no outliers, no extreme values. In other words, at the small sample size, the population has to be a bell curve or something close to it. Mound-shaped would be good enough on this. Our temperature's lower. Now, what I had to do on B and C is just make sure that you had, it would depend on which way you subtracted. So if you did after minus before, so this one minus that one, then you would have had an HR of mu less than 0. If, on the other hand, you did in the direction I have here and you subtracted before minus after, another way of saying that the mean after is lower is to say the mean before is greater. And though this was really what I thought, given the wording of the problem, was the best, I did accept this as well. But now when you went down to the next part, you had to match up with what you had here. So if you said mu less than 0, you should have had reject HO if t-test is less than minus for degrees of freedom of 6 and a one-tailed 0.5. You should have gotten 1.943. I'm doing that from memory, so let me look back and check that. 6 degrees of freedom, one-tailed 0.5, that's right. So those two go together. But if you had answered this here, you would have had reject HO if t-test greater than 1.943. So those would go together. The interval goes from minus 0.4 to minus 2.53. Are you confident that it's lower? Well, assuming, and I'm going to say that we did here, are you confident it's lower after administering the aspirin? The answer is yes, because all of the numbers are less than 0. In fact, it would have to be, if you look at the numbers here, that's the only way you could have subtracted to have gotten that interval. So, yes, the entire interval is greater than 0. You might note that if you looked at the previous test that I gave to the day class, that I gave them a matched pairs problem, and it had these exact same questions. Okay, so the final problem on this. And this one actually has the same questions as the last one, or virtually the same questions. I think they actually are the same, except for, and the scenario is different. In this one, there's a claim that 90% of all homes have at least one smoke detector. Detester. Oh well. It's getting a little late in the afternoon here. So we want to know if a concerted effort has raised that. So we have a sample of size 400. Of those, 376 have smoke detectors. Can we conclude that the population proportion, this is a qualitative variable, the no means and standard deviation, is higher than the national rate, greater than 0.9. That's the 90% there. And it says is it higher than the national rate. Sample size is large enough. Explain. Well, there were 376 said yes, and 24. That's just 400 minus 376 no's. So those are both greater than 5, so yes. Write the research and null hypotheses. I've kind of got that over here already. Write the decision rule that would be used for the critical value approach. Reject HO if anytime we have proportions at z-test, look at the research hypothesis greater than. So 0, 5, level of significance, go down to the bottom row of the t-table, one-tailed test 05, you should see 1.645. Write the formula that would be used and then enter the numbers into the formula, no need to calculate. So what I got a lot of on this one, remember I gave you the formulas for the standard errors, but not the whole confidence interval or test statistic formula. What I got a lot of on this problem was simply the standard error formula. That was, well, I think out of 2 points I might have given you a half a point on that. I don't know if I should have given you that, but I did. But anyway, z-test is equal to the sample statistic p hat minus the hypothesized parameter over the standard error, remembering that this is pH QH over N. And so the sample statistic was p hat, that's 376, let me write that down, divided by 400, which is 0.94. So our sample statistic is 0.94 minus 0.9 divided by the square root of 0.9. That's a 0.9. 0.1 divided by 400. And then for the 90% confidence interval, we're going to have the statistic p hat plus or minus z. I'm just putting the star there to designate that it came from a table. You can put that there or not. Times the standard error, but now it's, okay, not going to let me write there. P hat, so I'm going to go up here and see if it'll let me go up here. Plus or minus z times the standard error, p hat, q hat over n. And so we had 0.94 plus or minus for 90%, that's 1.645 times 0.94. It's the sample proportion. 1 minus that is 0.06 divided by the sample size of 400. And that's that.